lined up for this year, which we'll hear about in a minute. Society is currently, I think, as big as it has ever been, as far as we know, in terms of membership. So it's doing okay. If only the skies would clear for a little bit, so we can actually do some of this thing. But we're hoping this will happen this week. So before we get on with the next lecture, David is going to do his secretary's announcements.
Well, good evening everyone. Welcome to the new session.
I've signed it already.
There's a few events coming up already. The first one we have is a week tonight, which is the first meeting of the imaging group. This is an online meeting via Zoom. It starts at 7:30 and it lasts until 9 PM. And the undecided subject for this month will be one of our members, Guy Williamson, will be demonstrating his dwarf 3 telescope, I think that's what you call it, isn't it?
Yes, dwarf 3 smart telescope.
And including its imaging capabilities, its processing capabilities. So that's a week tonight. On the next event is on Saturday the 4th of October, which is an open day at ECMO, which is it's currently planned to run from 12 to 4 o'clock, although I think there's
2 to 6.
Oh, 2 to 6 is
2 to 6, yeah.
And the plan is to do solar observatory of the size of Cuba. So that's at the observatory itself. On Monday the 6th of October we have the Society AGM. This will be an online event. That's from 7 PM to 9 PM. Then on Thursday, the 9th of October, we have the first meeting of the beginners group, which is run by Chris and Lorna at Acre Road. Lorna, do we have a subject?
It'll be an introduction to the night sky.
Introduction to the night sky. Okay, that's fine. So that's at Acre Road. And then on Sunday, the 12th of October, we have the Observers Group meeting, which is run by Robert down here at the front. This is also a Zoom meeting online from 7:30 to 9 PM. So that's all the events for now. Also, just a reminder, membership fees are due, and you're in the middle of the you can take money tonight, can't you?
I'm always willing to take money.
Okay, that's fine.
There's membership forms dotted around if anybody's looking for a hard copy, or you could use the online version as well.
Did you say you get it back? So follow.
Okay, finally, I'm just going to use you of a couple of online events. This is probably something which will be emailed to you later, or some other time. It's a message from the Federation of Astronomical Societies. There's a couple of webinars that are coming up. The first one takes place on Saturday the 29th of October. It's presented by Professor Mike Brown of Caltech. And trying to find the subject. I think it's about the subject that the search for Planet 9. And then that's followed by one on Saturday the 15th of November, Professor Alan Stern, who will be talking about the New Horizons mission to Pluto. I've got some information here about it which I'll put down the front. If you are a member, there's a discount code as well, which you can also use. But tickets are available via Eventbrite. But that's details there. And that's all for tonight.
Okay, thank you, David. Just to reiterate, if this is a public lecture, so you don't need to be a member to be here tonight. If you are a member of the Society, then you'll get information about what David just told you via email and by logging into the website as well. If you are not a member of the Society and would like to participate, you're very welcome. There's no level of knowledge assumed. Beginners are very welcome. As you heard, Chris and Lauren are running a course for beginners, starting with introductions to the night sky out at the University Observatory at Acre Road, beginning of October. Beginners are very welcome to the Society. So, let me move on to the main feature for this evening. We're very fortunate to have Dr. Vicky Fawsett joining us. She's come up from the University of Newcastle. She did her PhD on red quasars. Yes, not blue quasars, red quasars. And she's currently doing her research at Newcastle University. And your speciality is active galactic nuclei, and you're actively involved in the MOONS project with a very large telescope. So some cutting edge stuff. And you're also in receipt of an STFC Spark Award for outreach. So we're very fortunate to have her along tonight. So Vicky, will you tell us about observing the brightest objects in the universe?
Yes, thank you. Everyone hear me okay? Great. Yep, so hi everyone, I'm Vicky Fawsett. I'm an astronomer at Newcastle University, and it's my first time ever visiting Glasgow, so very happy to be here. It's been on my to-do list for a while. So what I research, or what I'll talk about a bit, is quasars, but we'll kind of go into black holes to start with before jumping into quasars. So, just a bit about myself. I did maths and physics at the University of Warwick back in 2014 because I thought I wanted to be a mathematician, and at university I got more and more into physics, didn't really know what sort of physics, like nuclear physics, particle physics, I kind of dabbled in a lot. But then I ended up doing a master's project in exoplanets, it's kind of looking at X-ray data of four stars in a nearby cluster. I really enjoyed astronomy, but I wasn't sure whether exoplanets were really my thing. So I then went on to study a PhD at Durham University, which was COVID, that was great. But I did have a couple of non-COVID years, and I did travel a lot during those years. And I kind of switched to quasars, which are these really extremely bright galaxies, the most powerful objects in the universe. I really enjoyed that, so I just continued doing that. I'm currently a postdoc at Newcastle University. So as you can see, my mum used to joke that I was just travelling, moving further and further north, and that I would eventually end up in Scotland. But jokes on her, I'm moving to Germany. So I accepted a fellowship at the European Southern Observatory, ESO, which some of you are probably familiar with ESO. They're the ones that could build the telescopes like the VLT, and at the moment they're building the extremely large telescope. And so I'm hopefully should be flying over end of November to start that new session on the 1st of December, kind of just continuing doing what I'm doing at the moment on quasars. So, like I said, before we go into quasars, we're going to take a little bit of a step back. So, I'm sure everyone here kind of has an idea of what a black hole is. So, black holes are these incredibly dense objects. They're so dense and have so much gravity that nothing, not even light, can escape. And that's why they're called black holes. And how you form a black hole is with extremely massive stars, so about 25 times the mass of our sun. It gets to the end of its life, it doesn't have enough fuel to keep on burning, keep on shining, and it then collapses down into what first explodes as a supernova, and what's left over collapses down to a very tiny, tiny point, and this is what forms a black hole. So when our sun dies, it won't form a black hole because it's just not big enough. It'll form some other fossil star called a white dwarf. So there's two kind of important concepts of a black hole. You have the event horizon, which is kind of your classical kind of size of a black hole, and this is the point of no return. So once you're beyond the event horizon, even if you're in a rocket traveling at the speed of light, you will not be able to escape. You also have, and you see a lot of these kind of nice simulated images, you have this bright disk of matter, which we call the accretion disk. And this is a disk of material that's feeding the black hole. And much like the sun has gravity, that's why the planets go around the sun, because the black hole has so much gravity, you get all of this material kind of whizzing around the black hole, it rubs together, this friction causes heat, this heat causes light. So when we talk about observing black holes, we obviously can't see black holes by their definition, but what we can observe is this incredibly bright disk. And just to note, you often see, when you see these simulated images, this kind of circle, And that's because the gravity of the black hole is actually bending the light from the accretion disk behind it around the black hole, and that's why you form this kind of ring image. And people who are into films, this is actually an image taken from the film Interstellar, which is a great film. And the people that made Interstellar wanted it to be as scientifically accurate as possible, so they gave Kip Thorne, who won the Nobel Prize in 2017, gave him a load of money, some time on a supercomputer, and said, could you simulate a planet going around a supermassive black hole? So it has been edited to make it look a little bit more pretty, but this is direct images that came out of this supercomputer simulation. So all the things that happen on this planet around the black hole, the time dilation, 1 hour passes, 30 years pass on Earth, that's all scientifically accurate. Spoiler alert, the end is not accurate. If you're familiar with the film, it falls into a black hole and something weird with a bookcase happens. That wouldn't happen, but it's a movie, but it's a great film. So, because black holes are such weird objects, this is probably my favourite way to visualise them. So if you now imagine space-time as a blanket, and when we have different masses, such as a star, you can imagine like a football, you create a dent in this blanket. And the larger the mass, the more of a dent you're going to create. So now, if I'm another star or maybe a passing rogue planet, and I'm on a trajectory, what I'm going to do instead of just travelling straight is I'm going to come along this path, fall into this kind of bowl, and then I'm going to start to orbit this star. Or if I'm too close, maybe fall into the star. And this is kind of how you can explain the orbits of the planets. This dip effect is gravity. So now if we take a black hole, you can imagine pinching this blanket and then pulling it down to infinity. So now if I'm a star and I'm fortunate enough to come close enough to this dip, I'm going to fall into the black hole and I'm just going to keep falling forever. And that's another reason why they're called holes, because you can imagine them as a literal hole in space-time. So there's a thing in astronomy, we're really bad at naming things. For example, the very large telescope, extremely large telescope. So when you hear about people talking about supermassive black holes, that just means a black hole that is really big. So supermassive black holes are black holes that are about hundreds of thousands to billion times the mass of our sun. And quite a surprising discovery in astronomy that came in the last couple of decades is that we now know at the centre of at least all massive galaxies, there's a supermassive black hole at the centre, including our own, which is called Sagittarius A star. And how we grow these billion mass supermassive black holes? Well, we think it's via accretion, so this just simply means things falling into a black hole. They're fairly simple, they're exotic, but they're quite simple objects in the sense that if you throw mass in, the black hole gets bigger. However, this is actually a pretty massive area of research at the moment, is how you grow these supermassive black holes. And I'll come back to that a bit later, because the simple answer is we don't really know how you grow some of these supermassive black holes. So when I used to give this talk, kind of 7-8 years ago, I usually went through all the indirect ways that we know black holes exist, because it has been quite kind of contentious whether these weird objects exist or whether it's some weird form of gravity that's happening. And some people just didn't really believe black holes were out there. They were like, this is too strange. But now, as of 2019, we have an image of a black hole. So this was the first direct evidence that black holes definitely do exist, which is great because that's what my research is coming from. So the first one was this black hole in the centre of a nearby galaxy, nearby in the kind of astronomical sense, so 55 million light years away. And this was the galaxy M87, and this is the image we got. It's from kind of radio telescopes, and you can actually do a lot of physics with just this image. So we could measure the mass of this black hole, and we know it's 6.5 billion times the mass of our sun. And you see this kind of luminous ring of light. So this is the accretion disk. And like I explained with that simulated image, what you're seeing is the accretion disk from in front and from behind being kind of lensed over across the black hole. And you can do loads of other physics. We know how fast this black hole's spinning and all sorts of things like this. And then even more impressive, some would say, we took a photo of our own black hole, the Sagittarius A star. So, although this is only 27,000 light years away compared to 55 million, this was actually much more difficult to take a photo of. And that's simply because there's just so much material in our line of sight between us and the centre of our galaxy. It's really hard to image the centre of our galaxy. But they did it, and our supermassive black hole was a little bit more modest, so it's only 4 million times the mass of our sun. But you probably will notice that these two images, they look fairly similar, and that's despite this kind of pretty massive difference in the mass range. So 6.5 billion times the mass of our sun, 4 million. And that's because, like I said, although black holes are these exotic, strange objects, they're really only governed by kind of their mass. They're quite simple objects. They all behave in a similar way. So how did we take these photos? So it was something called the Event Horizon Telescope, so or the EHT. And like I've mentioned, these are all radio telescopes. And a cool thing you can do with radio astronomy is you can link different dishes up together, and the more dishes you link, the longer your baseline, you create a bigger telescope. So by linking these observatories from South Pole, Hawaii, Spain, Chile, others, we essentially created an Earth-sized telescope. And the resolution of this telescope was so good that if you had a credit card on the moon, the kind of equivalent wavelength, you'd be able to read the digits of this credit card on the moon from this telescope. And kind of a fun fact was that there was so much data, and they had to all be kind of taken to the same data center, they couldn't actually be sent electronically. So they had like FedEx vans delivering hard disks because there was so much data. So in my opinion, this is probably one of the greatest achievements in the last 10, 20 years. Even though when this was published, I remember being on Facebook, people were very disappointed and said it was just a fuzzy image. But it's actually very incredible that we managed to get this image. And I've been told that there's a third supermassive black hole that they've imaged. Given the time difference between these two, I maybe expect them to publish it in the next year, so keep your eye out for that. I'm not sure which one it is, but I'm sure they did image 3 of them, but if anyone has more info on that. Okay, so that was a bit of background. Moving on to what I study. I study these things called active galactic nuclei, or AGN for short. And an AGN is just a galaxy that has a supermassive black hole in the centre, but the surrounding material, this accretion disk, is so bright that it outshines all the stars in the galaxy. And we say a galaxy is active if it contains an AGN. So I just mentioned the Milky Way has Sagittarius A star in the centre, so is the Milky Way an active galaxy? Well, luckily for us, it's not. And that's simply because Sagittarius A star is just not eating much. There's not enough material at the centre of our galaxy to feed and fuel this supermassive black hole. So we live in an inactive galaxy. And if you saw an active galaxy kind of on the sky, so our Milky Way, like Andromeda, is a beautiful spiral galaxy. This, like I said, the centre of an AGN is so bright that you wouldn't be able to see any of that structure. It would just look like a point source on the sky. So, when we started discovering AGN, so we chose them to be these really bright point sources in the sky, we then started taking spectra, and I'll get on to spectroscopy a bit later. But what to take away here, so all of these, apart from the one I've highlighted in green, which is just a typical galaxy, all of these are AGN. And although you can see they have similar features, they have these or we call emission lines, but there's quite a lot of variations. So some are more narrow, some of them are very broad, some of them you don't really see any features, and as you can see, each of these have a different name, which I won't go into, but some of you might be familiar with Saphirds, quasars, which I'll talk about, liners, blazars. People started naming all these different subclasses, and then it became what was called the zoo of AGN. So many different types of AGN kind of got a little bit out of hand. So back in the 90s, people came together and said, what if all of these different types, different flavours of AGN were the same physical object, we're just looking at them in different ways? So this is slightly complicated, but essentially this is your model of an AGN. You have a supermassive black hole, you have your accretion disk. Slightly further out, you have what we call the dusty torus, or the dusty donut. This is just a donut shape of kind of dust that surrounds your accretion disk. And then you can sometimes get these highly relativistic jets launched from the black hole. You don't always get them. So then, what they said is that depending on our viewing angles, so obviously we're on Earth, we can't fly to these objects, go like round the back and take different pictures, we just have the same kind of angle. If you're looking down the barrel of the jet, the light that you're going to observe is going to be very different if you're looking through the dust or straight at this accretion disk. So this is my first video, which hopefully will work. Yes, wow. So this is a little video zooming into an AGN. So you can see the kind of bright central source. We're going to go right into the nucleus. So this is the kind of dusty torus that I was talking about. And what this video is trying to demonstrate is, imagine this is our telescope line of sight. So right now, we're looking through the dust. It kind of blocks out most of the light from the accretion disk. And now as our line of sight moves above this dusty donut, we're going to get more and more of the light from this incredibly bright accretion disk. So you can see that depending on your viewing angle, the light that you observe with your telescope is going to look very different. So this is kind of the textbook model. If you do physics undergrad, they will show this kind of little cartoon. So this was called the unified theory of AGN. And like I said, this just said all the different types of AGN are intrinsically the same object, it just depends on viewing angle. And all you need to know is that quasars, which is what I'll be talking about, has this unobscured beauty accretion disk. And that's why they're the most powerful objects in the universe, because we're directly observing this very, very bright accretion disk. So, what is a quasar? It is just simply the most luminous, the most powerful type of AGN. And the most powerful quasars we've ever discovered, I think the brightest one ever was discovered last year, 2024, there's a paper, which was about 10 to the 41 watts, which is roughly 1,000 times brighter than the Milky Way. So you imagine 1,000 Milky Ways and you can put them all together, that's how luminous some of these objects are. So why are they called quasars? So quasar stands for quasi-stellar radio source. And this was because when they were discovered in the 60s, they were discovered using a radio telescope. So they were these very bright kind of point lights, they looked like stars, radio sources. And astronomers were a little bit puzzled at the time. They thought maybe this is a new exotic type of star, this like radiant bright star that we're observing. So they called them quasi-stellar, so star-like radio sources. So we now know that they're not stars, they're actually kind of massive galaxies with this really bright core, and that's why they look like point sources in the sky. So sometimes you'll see them referred to as QSOs, which a lot of people prefer. This stands for quasi-stellar object, so it's just trying to get away from this radio definition. Because although quasars are typically quite luminous in the radio, they're luminous across the electromagnetic spectrum. So it isn't just the radio that you can detect them. So why do we care about quasars? Well, probably the best example is cosmology. So I'm not a cosmologist, but I do recognise they're useful for cosmology. So because quasars are the brightest objects in the universe, we can see them the furthest away. Because they're so bright, we can use our telescopes, and as things get fainter and fainter, we then can't observe them, but quasars are really bright. And in astronomy, the further away that you observe, the further back in time you're observing. Because light doesn't travel instantaneously, it's pretty quick, but it does have a fixed speed. So the more distant the object you can observe, the closer to the Big Bang you're probing the universe. So what cosmologists do is they like quasars because they're essentially like lampposts looking back in time. And the whole point of the cosmologist is they're trying to see how do we connect the Big Bang and model that forward to the sky that we see today. And quasars are one of the best probes of the early time of the universe. And I had to double check this because the James Webb Space Telescope keeps breaking records. But this is still, I believe, the most distant quasar ever discovered. It was discovered in 2021, so I'm sure it's going to be beaten soon. This is the lovely named J031-1806, and this quasar is about 13.2 billion light years away. So because astronomers use really stupid units all the time, we don't have to because the distances are so large, but they're kind of meaningless sometimes. So for people that don't know, a light year is just the distance that it takes light to travel in 1 year. But doing some quick maths, so don't correct me if I'm a little bit off. 13.2 billion light years is roughly 1.3 times 10 to the 23 kilometres, or that many kilometres, if you prefer, which I can't remember how to say. Now, if we take our fastest spacecraft, which I believe, do correct me, is the NASA Solar Parker probe, it goes around about 150 kilometres per second. We use a little bit of maths, and we work out if we sent this satellite off to this quasar, it would take 27 quintillion, I think that's how you say that one, quintillion years to get there. So I guess this just kind of demonstrates how big space is, but also a difficulty for astronomers. So most physics, you have a theory, you go to your lab, you test that theory, you get some results. In astronomy, we just can't even send probes or robots out to any of these objects. We have to just go based on the light we receive from telescopes, which is why astronomy is kind of evolving all the time, because the better your telescope, the more data or the better quality you have. And that's why some papers can be wrong, but it's also why I find it quite exciting, because it's always evolving. So this is the actual paper, this discovery, again another stupid quantity, unless you're an astronomer. So this is at a redshift 7.6, if you like redshifts. And this is linking back to my earlier point about growing supermassive black holes. So in the abstract, they actually say that they've discovered this quasar, they measured the light, they measured the mass of the black hole. There is always uncertainty when you do that. And they find that it's about 1 billion times the mass of our sun. But then they say the existence of such a massive, supermassive black hole just at 670 million years after the Big Bang challenges significantly theoretical models of supermassive black hole growth. So what they're saying, what they say in the paper, is that if you take our models of how you grow a black hole, you set it to maximum, you do a simulation, and you even are quite generous, you say that that black hole popped into existence straight after the Big Bang, and you let it grow for 670 million years, you cannot grow a 1 billion mass supermassive black hole with our current models. You just don't reach those masses. So there's a lot of work going into this at the moment. It's one of the main goals of JWST, the James Webb Space Telescope, is trying to probe the early universe, trying to measure these early supermassive black holes to see if we can come up with better models of supermassive black hole growth. And we do have a couple of theories that I'm happy to talk about afterwards, but kind of the simple answer is I don't think anyone's really solve this yet. I went to a conference recently, lots of talks on this problem, people with ideas but no kind of substantial evidence of how we grow these black holes. So if anyone has any ideas, then maybe there's a Nobel Prize in it for this problem. So how do we study quasars? So in my work, and lots of people's work, like I said, they were originally discovered in the radio, but they're so bright you can observe them in pretty much anything, in optical, gamma rays, X-rays. So in my work, I combine optical and radio, mainly. So previously I've been using the Sloan Digital Sky Survey, or SDSS, that's been running for 25 years now. And in the latest data release, about 750,000 quasars. But recently I've been more and more involved with the Dark Energy Spectroscopic Instrument, or DESI, which I'm sure a lot of you have heard of. And this will eventually have 3 million quasars. And I believe it was something like in the first 2 years of observations, DESI already overtook SDSS, which had been going for 20 years. So this is SDSS, it's on the Sloan Foundation Telescope in New Mexico, 2.5 meters. This is the only bit of instrumentation. So don't ask me too much about instrumentation, but I know a lot of people here probably are interested. And then DESI's on the Mail Telescope in Kitt Peak, Arizona, bigger telescope, 4 meters. And why DESI so good compared to SDSS? So this is an SDSS plate, and what you can see is all these little holes. And so for an observing light, you'll punch holes in your plate, and then you'll feed in fibers to point at different objects in the sky. And you have to feed them in manually. SDSS and upcoming, what we call multi-object spectrographs, have robotic positioners. So this is the SDSS kind of, these called PET, what the whole thing is called. And here's a little movie you might just be able to see. These are the little, they're each holding a fiber, and basically you can just configure them all in one go, say, these are my observations, these are my galaxies I'm going to look at. You press play, they will move into place, and it takes a couple of seconds or something. I mean, I don't know too much about the programming. I have heard that this took a long time to make work because you can't have your little robots colliding because that will damage. Apparently this was a big problem, trying to stop them colliding whenever they moved. So loads of work also went into the program to make sure that it doesn't damage itself every time it moves. But that's why it's so efficient, because you don't need people plugging in. It just, you can automatically configure it and then change to a different position of the sky quite easily. Okay, so I'm mainly doing spectroscopy, and I mentioned spectra earlier. So everyone here knows what a spectrum is. Well, at least in the astronomical sense, it's light split into different wavelengths. But a better question is, why do we use spectroscopy when we have imaging? So there's a lot of beautiful images in astronomy. I remember at university, one of my lecturers said, don't get into astronomy, you just want to look at pretty pictures. But it is kind of looking at a lot of pretty pictures. But yeah, why use spectroscopy? So here I have an example of an AGN, a star, a galaxy. So the AGN, I've cheated a little bit because I've also, this is a composite image with some X-rays. But you can see these powerful jets launched from this, and the really bright central source. So this is clearly an AGN. This diffraction spike and this point source is clearly a star, and then this is obviously a nice spiral galaxy. And with probably very limited training, you'll be able to visually identify these objects. And that's all really nice. But the caveat is these are all really, really nearby objects. So you do have astronomers that work on nearby objects because you get much better data. There's somebody in my group that has JWST imaging of some nearby AGN, and the data is beautiful. These are the objects I look at. So this is real real images that I took from an imaging survey, and I've selected a galaxy, a star, and an AGN. So I'll give you a couple of seconds if you can guess which one's which. But basically, you can't guess, because you might say, oh, there's slightly different colours, but stars, galaxies, and AGN come in all sorts of colours. But if I take a spectrum, and again, this is DESI data that I also pulled down, the main thing to take away is that all three of these spectra look really, really different. So, although these just look like blobs in the sky, we can't really distinguish them. If you take a spectrum, they have very, very distinct features. So, like a star has, because this is a cold red star, it has absorption features. Quasars have these really strong, broad emission lines. Galaxies don't have broad emission lines, but they still have strong emission lines. You can see one here, but they're much narrower. And even if you don't know much about visually identifying spectra, you can feed this into